Okay. For a smidge of review, now we're not going to be able to review confidence intervals today because I want to start hypothesis testing, but we will have opportunity to do more confidence intervals later. So just as a, I guess it's not really a review, it's more of a reminder that last day we did confidence intervals, or I guess one confidence interval for one sample proportions, right? And so we established the rules and things for this first type of question that we're going to have, which is one sample proportions. We said, well, if I have some point estimate, my p hat, then I can go down a little, up a little by some number of standard errors. And so we talked about how do I find this Z star or this critical value? And then I multiply that by p hat q hat over n. Right? And then we had to interpret that interval, and that was all fun and games. And then we said, okay, the second part of inference, right? First part is a confidence interval, nice and breezy. And then the second part of inference is the more formal hypothesis testing. So this is 5.3, I think. Now, just as a side note, because there are Monday labs, might have been confusing to start lab 7. That's kind of the curse of the Tuesday, Thursday section is we don't have time to introduce things before the Monday lab. But for lab 7, Q1, so question 1 is a confidence interval, which you can do, but question 2 is a hypothesis test, which we're just going to do today. And so if you tried it and you looked at it and thought, oh boy, that's tricky, that's okay, we haven't done it yet. But the due dates are kind of far out for that reason. Far out. Hypothesis testing. Okay. Which is what we're doing today. Now, I'm going to be adding a bunch of notes in between the slide notes. So sometimes I like the slides. Some terms they work for me, and this term I'm like, I want to do it differently. So I'm just going to do that. I'm going to go rogue here. Oh, let's see if I can add some lines maybe. How do I create a template maybe? No. I want, okay, let's see here. No, I can't. I can't do it, I'm too little. Okay, just like a child, I give up. I can't get lines on my page, oh well. You'll have to put up with it. So hypothesis testing is the meat and potatoes of this course. I know I said that about inference, but really, ultimately, inference is hypothesis testing. It's whenever we want to establish significance, right? And so you want to be able to say something like product A is significantly better than product B, right? The proportion of people who will vote for candidate A is a majority. That's useful, right? Significantly more than 50%, right, is what that implies. And so whenever we want to establish significance, we have to do a hypothesis test, a formal hypothesis test. And so hypothesis testing is we want to formally establish significance. We want to formally establish significance. It's also called significance testing, right? But we are testing a hypothesis, and so we'll call it hypothesis testing, which is more proper. Let's say you're in a job and you're up for, you're competing for a promotion. How are you going to be able to say, well, I sold significantly more than my counterparts? Can't just say that. I guess you could, but then your boss would say, oh, really? Okay. And so then you want to have the formal test to back it up. So for example, if you want to claim that I sold significantly more, whatever. I guess you're in a sales job. No, it'd be funnier if you weren't in a sales job. You're in healthcare. I sold this much stuff. Okay. Anyways, I sold significantly more than other employees, for example. But the key here and what we're latching onto is this significantly, right? You might sell significant, or you might sell more, but not significantly more, right? And so that's where this hypothesis testing comes in. Which I'm going to abbreviate HT because that's really annoying to write. And so hypothesis testing is HT. Okay. Now, I think I've warned you that inference is like learning a complicated game. But once you learn the rules, and there's a lot of them, okay, you'll be able to play all the games, all the different types of questions, right? And so we're going to spend a lot of time here establishing the rules. And then what you'll see is that they apply to all the different types of questions. Okay, and so it's worthwhile to learn the rules, obviously, mostly to pass the course, but also it's not that strange if it feels like a lot now when we're first introducing these things. So just know that we're going to be doing this a lot, and we're going to be picking up on little techniques along the way. And so for me, when I'm learning, I always like to have a general overview and then go back in and fill in the pieces, right? And so I always found that it's easier to study for a final exam just because I know what the end goal is, right? I just need to learn all those things, and I know where we're ending. And isn't it so easy? You just have to learn all those things. And then, so I'm going to use the same approach for introducing hypothesis testing, because there's a lot of ins and outs and a lot of things to keep in mind. But I want to give a general overview and then go back in and fill in the cracks and so on and so forth. And then we'll have an example. But if my earlier section is anything like this one, we won't have time to do the example until Thursday. So that's okay. Like I said, nice and slow. So in our situation, for our one sample proportion, which is the only type of question that we've introduced so far, and where we're going to be spending a lot of time and establishing these rules, what do I have? Well, I have collected a sample. I have a sample proportion. And what would I want to know, right? What would I want to kind of show significance for? Now, I only have one sample, and so I would want to compare it to some hypothesized proportion, right? Is it significantly more than 50%, right? Is this candidate going to have a majority vote, right? For example. And so I have a sample proportion. And so we want to compare the sample proportion, which is p hat, the sample proportion p hat to a hypothesized population proportion. To a hypothesized population proportion. I may as well introduce it right away because we're going to be using it a lot. This hypothesized population proportion is going to be denoted by a p subscript 0. So it's still a proportion, so it's a lowercase p. And to denote that it's from the hypothesized population, we're going to use a subscript 0. P subscript 0. So it's a lowercase p because it's a proportion. And this is P naught. And I can't remember if naught is NOU or NAU. Null. You can say P null or P NA or NO? N-O-U-T? Oh, let's go with N-O-U-G-H-T. Not. You just say it as not. Or N-A-U-G-H-T. Anyways, whatever. There. Throw it on there. Doesn't matter. P naught. This, it'll become clear why we use a subscript 0, right? But I think of the subscript 0 or the P naught as, okay, this tells me that this is from this hypothesized population, right? A lowercase p is just a population proportion. And so this is a special population proportion from the hypothesis. Okay, now I want to kind of show you hypothesis testing without, what's that? Tell me you're doing hypothesis testing without doing hypothesis testing. Here we go. So what's hypothesis testing? Well, I have some sample proportion, right? I want to know, does it come from a population where the proportion of votes is more than 50%, for example, right? Maybe I want to know, is it less than 50%, right? If it's the kind of the opposite candidate of who I'm interested in, right? Or is it just different from 50%, right? And so the different scenarios that we can have are, okay, these populations are going to be centered on P naught now, my hypothesized population. That's what I think my population looks like, okay? And what I'm gonna have is, what if I have a P hat? Or maybe let's do this. I'm gonna scoot this to the middle here, and let me make it a little more clear. What if I have a P hat here? Intuitively, would you say that this P hat is significantly different from P naught? Probably not. Let's dig deep. What are you kind of basing that off of? I'm gonna tell you, because it's not very far, right? That's what you're using. But then also, I'm gonna tell you the background of what you're using. Well, the probability, which is the area under the curve, the probability of seeing something more extreme than this is quite large, right? There's wiggle room here that's still hanging around P0, P naught, right? What if I threw down a P hat, so a different sample proportion up here, right? And I asked you, okay, let's call this P1 hat, and let's call this P2 hat, or A, B, whatever you want. So now I've got the second scenario, and it's out here, which is, to me, quite far from P naught, right? So then you kind of ask yourself, okay, do I think that this P2 hat, do I think that this came from a population centered on P0 or P naught? Probably not, right? It feels unlikely. Feels more likely that it came from some other population. That's fine. We have room for that in our hypothesis test. Okay? And so what we're going to say is, well, it's possible, right? It's still, you know, these tails always keep going to negative infinity, positive infinity. So there's always a possibility, right? But the probability of seeing something as extreme or more extreme in this case is very, very small. Okay? We're going to start calling that the p-value. And I'm introducing it now with all these other p's, but it's good to get all the p's out of the way, right? And so the probability, which is an area under the curve, is the p-value. Okay? It's different from p, p hat, p naught, right? And so here, let's say, maybe let's just write down what I just said. So consider P1 hat, right? Because they're close together, but also that links to the probability of seeing something more extreme than P1 hat, right? Then we say that it's not significantly different from P0, right? And so the probability of seeing a sample proportion as extreme or more extreme than P1 hat, P1 hat, assuming the population is centered on P naught, the population is centered on P naught, is large, therefore, they're not significantly different, right? You want that probability. You want them to be far apart to be able to say that they're significantly different. Now, we don't talk about the distances mostly because imagine telling your boss, oh, well, it's because it's this many standard errors away. That's hard for our brains to kind of wrap our heads around. So we would rather talk about, well, the probability of seeing something more extreme than what we saw is 20%, which is not significant, right? And so it's really just a matter of this formality that we're introducing here is really just a way of communicating these results. We could talk about, well, because of this distance being very small, right, then there's no significant difference, right? But we take it one step further and latch onto the probability instead. Right? Okay. What was I saying? The probability of seeing a sample proportion as extreme or more extreme than P1 hat, assuming the population is centered on P naught, is large. So we conclude they're not significantly different. So we conclude P1 hat is not significantly different from P2 or from P naught. I almost introduced P2 hat. All right. There's that word. Significantly different. They're different. You can tell they're not on top of each other. That can happen, but it's unlikely. Right? They're different, but not significantly different. Right? And so what about the other one? Well, now on the flip side, if we consider P2 hat, we're saying that, okay, well, let's talk about in terms of the standard errors here, right? It's quite far from P0 or P naught, right? But then we say, okay, to communicate that better, I'm going to talk in terms of probabilities. The probability of seeing something a P2 hat or more extreme, assuming that it's still centered on P0, that probability is very small, right? And so that's why we say, that tells me that P2 hat is significantly different from P0. So the probability, let's remind ourselves actually, what is the probability? The probability is an area under the curve. That's a good one to have up our sleeves. The area under the curve. And I know what you're thinking. Oh, phew, I already know how to find that. You do, using the tables, right? Or Excel or some other software, right? You can calculate a Z-score. Hey, I'm giving it all away, right? You can calculate a Z-score. How far is your sample proportion from your hypothesized proportion? And then you can link that and find probabilities, areas under the curve. And then if the area under the curve is small enough, you can reject the null hypothesis. But I get ahead of myself a little bit. Wow. It's all today. The probability of seeing a sample proportion, I'm just copying out what I said earlier, and I guess I could actually copy it. You know what? Save my poor wrists just a little bit. Of seeing a proportion as extreme or more extreme than P2 hat, I'll just swap it for P2 hat, assuming that the population is centered on P naught, is very small. So we conclude P2 hat is significantly different from P naught. But it all stems back to essentially how far away from each other they are, right? There's some wiggle room, but once you hit a threshold that we'll talk about, then you say, I think it's more likely that it came from a different population. Okay. So let's see here. I think it's worthwhile introducing the p, and I'm going to need another page here. A page. Going to need many more pages, but I think it's worthwhile introducing what we're going to call the p-value. mostly because it's confusing, right? We've got P, the population proportion. We've got P naught, the hypothesized population proportion. We've got P hat, which is the sample proportion, right? We've got a lot of P's piling up here, and the P value is different in the sense that it's a probability, okay? And so it's the probability which is an area under the curve it's the probability of seeing something as extreme or more extreme. Hey, isn't that exactly what we were saying up here? That's exactly what we were saying, right? So our conclusion is going to rely on the p-value, and that's why we're introducing it now. Need a little bit more space. The probability of seeing something, I'm going to start to make it a little bit generic. Now, in our case, this something is a sample proportion for now. Next type of question, that something will be something else. P1 hat minus P2 hat, the difference between proportions, and so on and so forth. So that the something is going to change, but seeing something as extreme or more extreme, this tells me that it's the area in the tail, right? So as extreme or more extreme, right, from here, and then more extreme relative to where you are on the curve, right? If you're above P naught, then more extreme would be into the upper tail. If you're below P naught, then more extreme is into the lower tail. So it depends, right? So this is the area in the tail specifically. Seeing something as extreme or more extreme than what we saw in our sample, what's one of the things that we're hinging all this on? We're hinging all of this on, okay, well, we're actually assuming that it's centered on P naught, right? And so we're assuming that this null hypothesis is true. We haven't introduced the null hypothesis, but we will, right? And so assuming that the hypothesized proportion is true, or in then what we saw in our sample, assuming the hypothesized population is true. So assuming that the population proportion is P naught, right? So assuming that it came from a population centered on P naught. Okay. That feels lofty, theoretical, and it is, right? But I want to introduce the 4 steps of hypothesis testing, and you can break it down. I like 4 steps because for me, 4 is a nice way of breaking things down without getting too nitty gritty, right? And so I use 4 steps. You can make it 7 steps. I think I've even seen 14 steps, but that's too much for me. So you can make it as many steps as you want. I'm going to write the steps down. I always write the steps down. You don't have to. It's just to show you that we're always following the same steps. So today we're going to introduce what those steps are, just in a broad sense. So there are 4 steps of hypothesis testing. I'll do HT. The first step is to state your null and alternative hypotheses. Now, what are those? Okay, well, that's a good place to start. State the hypotheses. Oops, gosh. Okay. In order to prove, now I'm gonna not use the one sample proportion example yet. Had to think about it. No, I stand by. In order to prove that product A is significantly different from product B, what do you have to do first? You first have to assume that they're the same until you have proof otherwise, right? And so your null hypothesis is always going to be a statement of no change. And it's going to be the thing that you assume until the end when you have evidence against it and you can say, that's not actually how it is, right? But so the null hypothesis looks like this. So you're going to use an H subscript 0. Uh-oh, that's where that P naught came from, isn't it? It is. Okay, so this is the null hypothesis. So it's H naught. I'll just make my A kind of look like an O and tail as old as time. Because I don't know how to spell it. I should have looked it up. What is the null hypothesis? The null hypothesis is a statement of no change. It's with it. Thank you. Now I can be clear. Good. Just thinking about how many times I spelled it with an O. I have to go back and add a little back on it. So the null hypothesis is a statement of no change. Is a statement of no change. That's cryptic. I know that. But first, if it's a statement, then your null hypothesis is followed by colons. And I only, it's not the end of the world if you use an equal sign here, but it's not an equality, it's a statement. Okay, so it's kind of a pet peeve of mine, right? And if you catch me on a bad day marking, I might take half a mark off. Oh, that's not good because it's a statement, right? And so it's pretty funny. Everyone, well, yeah, most of my coworkers, oh, you do your marking, you have a glass of wine, and I can't do that because I just get really mean. I'm not like mean or anything, but as soon as I've had one, I'm marking, I said this in class. So for your sake, I don't. But be nice. Depends on how I'm feeling, I guess. So it's a statement. So you have to use your colon. What do you want to make a statement about? In this problem, right, we want to hypothesize about the population proportion, P. So let's make a statement about P. Well, okay. That's good. But Emily, I wouldn't have got there on my own. Don't worry, it's on your formula sheet, but I'm not showing you quite yet. And so our statement for a one sample proportion question is, how does my population proportion relate to this value, this null value, right? My P naught. And I have to assume that they're the same, right? And so here's where the no change comes in. Right? I have to assume that the proportion of voters voting for a candidate is this proportion, is 0.5, until I have proof that actually what I saw was far enough away from 0.5 that I can conclude that it's different from 0.5 or less than 0.5, right? And so this is always going to be the null hypothesis for a one sample proportion question. Okay? That's nice. The only thing is that this P naught is going to be some proportion that you want to compare your sample proportion to, and it's from the question. Okay, so here, let's write that down. What color? I guess this one. P naught is the proportion we want to compare our sample proportion to, right, from the question. So you're going to grab that from the question. And so the question might be, okay, they found 54% said that they would vote in favor of this candidate, right? That's a sample proportion. And what if you want to show, well, is that significantly more than 50%, right? Is it a majority? So then the value, the P naught that you want to compare your sample proportion to is 0.5, right? Depends on the spread. But for now, it's just going to be some value that you want to compare your sample to, and it's in the question. Okay. If I, yeah.
What's that third last word?
From. Thank you. Uh-oh, looks the same. I rewrote it, but at least I'm consistent. So if I have a null hypothesis, I am also going to have an alternative hypothesis, right? What if I find evidence against this? Then I should have a backup plan, right? And so my alternative hypothesis, I use HA, depending on what field you're in, you might use H1. Oh, crazy, 0 and 1. I like A because it tells me that it's the alternative hypothesis. And so it's the alternative hypothesis. Now, it's not always the case, but usually it's the thing we want to prove, right? So we want to prove that more than 50% of voters are going to vote in favor of this candidate, right? That's what we're really interested in. I want to show that I sell significantly more than my coworkers, right? And so then what do I have to do? I first have to assume that I sell the same amount, prove that the distance between us is so large, right? Attach a probability to it, and done. No, not that easy, but in spirit, it is. So the alternative hypothesis is usually the thing that we want to prove, right? So is usually, oops, the thing we want to prove. Not always. As a quick example, right? I do 2 versions of the test. Then I wouldn't be doing my job if I didn't check to make sure that they weren't significantly different in terms of grades. Then I'd be in trouble, right? If one version was actually easier than the other, or, you know, whatever, one was harder, same thing. What would I have to assume? I first have to assume that the grades on the 2 versions, they're the same, until I find that, these average grades are different from each other. They're significantly different from each other. That's one of the scenarios where I'm really hoping that I don't reach HA, right? Or the alternative hypothesis. But we'll get there, and I'll show you that example with some data that I have from previous terms. Don't worry, they're never significantly different. That's such a relief for me, because then I'd be in trouble. Steve, who also teaches math and stats here, he often says, oh, the yellow version, that's the harder version, but that actually can impact the grades. Just thinking that you have a harder version, they're the same. So I don't do that. Okay. Well, I'm kind of in a bind here. I still want to talk about my population proportion and how it relates to P naught, right? It doesn't make sense to talk about anything but. So these 2 values are the same, right? The only thing that changes is this equality, right? Or inequality, rather. And so we have P, how it relates to P naught. So that all stays the same, but the only thing that changes is I'm going to throw a not equal to in there. We've got other options, but this is the only thing that changes in HA from H naught. Okay. You still want to talk about how the population proportion relates to 0.5, for example, right? And so all that's changing here is the sign. Okay. We actually have 3 options here, right? I've already used up the equals, so I can't have equals, right? And here, the obvious other one, the obvious flip side would be not equal to. All right, that's fine. What if I wanted to prove that it was significantly less than 0.5, right? So this sign is going to come from the problem or from the question, right? And so less than 0.5, then I would reflect that in my sign here. What if I wanted to prove, and usually in terms of voting, we want to prove that it's significantly more than 0.5, right? And then I would change this to a greater than, or the default is not equal to. If you're ever unsure, right, just use a not equal to, because it's going to be the safest thing. So I want to show you what these things look like. Okay, and so we have the sign in HA can be, depends on the question. So I want to know if it's less than, or if the question asks me if it's greater than, right? A majority would be significantly more than 0.5, right? And so, and then whether, if there's a difference, a difference means you don't care which direction it's going in, right? This less than, greater than, difference is going to be the area in the tail, right? It's going to be reflected in the tail. So I've got 3 scenarios, and to keep it all fair, copy. Oh, I should have put my P naught on there. Paste, paste, paste. 3 scenarios. I always assume that it's centered on P naught, right? Because I have to assume that the null hypothesis is true until I have proof otherwise. And so all of these are centered on P naught. And what we want to, so P naught is the value that we want to compare our sample proportion to. Now, if I want to prove that something is less than 0.5, let's say, I can't use 0.7 to prove that it's less than 0.5, right? I think we can all agree that that doesn't make sense. And so, of course, your sample proportion is going to have to be somewhere less than P naught, right? If you're trying to prove that P is less than P naught, which is going to look like this, your alternative is that P is less than P naught, then of course you need your P hat to be less than P naught in order to prove that. It might be less than, but not significantly less than. That's for us, that's our job to find out. If we want to know, and maybe I'll give myself a little bit more room here. If I want to know, is P greater than P naught, again, then my sample proportion has to kind of lean into that. And so then my sample proportion would have to be greater than P naught. We just don't know if it's significantly greater, right? If there's a difference, this is the tricky one. You only have one sample proportion, right? And we saw the sample proportion can either be below P naught or it can be above P naught. If you don't care which direction it's going in, if you just want to know if there's a difference, then whichever tail this P hat happens in, let's say it happens down here, what we do is we pretend that it also could have happened up here. We would be just as concerned if it happened in the upper tail, right? What we're going to be talking about are the areas in the tail, okay? And so here, right, that's our p-value, the probability of seeing something as extreme or more extreme, and our conclusion hinges on the p-value. And so that's why I'm introducing it here nice and early on. If I want to know if P is significantly greater than P naught, then that p-value has to be small enough, right? And I didn't write this one down. HA P not equal to P naught. It's going to happen in one of the tails, but then you replicate it in the second tail. These are called one-sided or one-tailed tests. One-sided or one-tailed tests. This is what we call a two-sided or a two-tailed test. I use them interchangeably, but I do lean towards two-tailed, one-tailed, just to emphasize that it's the area in the tails. And this is the default. So if you're ever unsure, right, then you're safer to use a two-sided test, right? Just test to see if they're significantly different from each other, right? And that's safe. Okay. Good. Is there anything else I wanted to say here? I know what I wanted to say, but I also want to skip it for a little bit. So once we have our null and alternative hypotheses, I know 4 steps, that was only step 1. Oh boy, I introduced a lot of the ideas here, right? Really, all you have to do in this step is state the null hypothesis and state the alternative hypothesis. And then I like to make a note to myself, whether it's a one-sided or a two-sided test, or a one-tailed or a two-tailed test, just because we'll need it later in step 3. So that's kind of a disconnect. Okay? But I'll introduce that later again. So now that you've set out your hypotheses, what you should do is you should check the conditions. So to make sure that you can still use this normal distribution that I've been drawing, right, then we have to check the conditions. They change ever so slightly, but I'm going to parking lot it for now because I want to get through all the steps of hypothesis testing. And so this is where check the conditions for the central limit theorem. So that's where you would sneak those in. But I'm going to say we're going to skip this for now. Okay. All right. Is it just me, or is it really hot in here? Just me. I don't have that excuse. Oh well, just hot. Wait. Okay, that's all right. I'd rather be warm than cold. So, step 1, done. Step 2, what could it possibly be? Well, if we think about, if we go back to up here, how have we decided whether, so we decided P1 hat is not significantly different from P naught. We linked it to the area under the curve, but in between there, that step that we did was to figure out, well, how many standard errors is P1 hat from P naught? And so that's our second step. We need that gateway in order to attach a probability to it, right? So same thing here. How far apart are these values once I take into account the spread? So, and maybe I'll put it on a fresh page here. Step 2 is technically calculate the test statistic. Now, I usually call it do the test, but then when there are questions that ask, hey, what's the test statistic? People are thrown off by that. And so I'll say it here, calculate the test statistic. Which I call it do the test. I think it's more fun, kind of an easier approach. We do the same thing, obviously, but the test statistic in this case is going to be a z-score. That's all we know how to work with so far. We can find probabilities associated with z, and so that's really nice. And so from the formula sheet, where is it? Here, we're working here with one sample proportion. We did a confidence interval. Hey, how nice is that? I give you the null hypothesis, right? And you know that the only change to the alternative hypothesis is the sign here, but that depends on the question, so I didn't bother putting it on the formula sheet, right? And so here, once you've decided that this is the type of question that I have, this is your null hypothesis. You just need to find the P naught, the value from the question. Then below that, I make you calculate the test statistic, which is a Z in this case. Now, I just want to give you a little bit of a heads up. The reason I'm being vague and just calling it a test statistic is because there are other test statistics that we'll be able to calculate. So just put some blinders on for two sample proportions, which is next, and just focus on, we're going to calculate a Z. Once you have a Z, you know what to do with that. Don't look at this. Don't look at that. That's for next week. Oh, so soon. Then we move on to calculating a chi-squared. Then we're going to calculate, I'm skipping some stuff. We're going to calculate a T, and a T, and another T. And if we have time, an F. And that's probably it, right? So there are other test statistics that we'll introduce, all in good time. Oh, I need to copy this. Little copy pasta here. Copy. So from the formula sheet, we've got this. So here, this is the test statistic. Whoops. For this type of question. So this is the test statistic. As we said, that thing is going to change, but how it behaves is the same. Okay. All right. What did we do before when we just had kind of that theoretical, okay, I've got this P hat way out here. How far is it from P naught? Well, that's exactly what we're doing here. We're taking how far is P hat from my hypothesized proportion, taking into account the spread, the standard error. Notice that this is only slightly different, but it is different than the standard error for a confidence interval. So that's kind of confusing in the beginning, but this is the standard error for the hypothesized population. Yeah. So this is the standard error of the hypothesized population. At its core, though, we've got a P times a Q divided by N and then a square root. That's the same, right? It's just that now we're using P naught instead of P hat because we have this hypothesized distribution. Okay. Now, without an example, it's hard for us to do anything here. So I'm going to leave it. But once we have a Z, right, I know how many standard errors away my sample proportion is from my hypothesized proportion. That's nice. That's nice. That's just a fact, I guess. Anything else I want to do here? No. Step 3, then, is now I can use this Z to find the area in the tail, right? And so what does that mean? It means I'm finding the p-value. So step 3 is find the p-value, which is the area in the tail or both tails if you have a two-sided test, right? That's where it stems back to the alternative hypothesis and the sign in the alternative. Okay, so finding the p-value is we have to find the area in the tail corresponding to the alternative hypothesis, which is way back in step 1. corresponding to HA from step 1. And so maybe what I'll do is I'll just snag those images that we had, right? And just reiterate that these actually belong, or these are helping us later. Right? Depending on what our alternative hypothesis is, right? Then, made it worse. That's going to determine how we find that area in the tail. Now, if you have a Z and you've drawn this all out, right? Your P hat becomes standardized to a Z. Now the Z is the same here. This just becomes a Z. You know how to find these areas using the Z table. And that's totally fine. That's one way to do it. Yay. Sounds like I'm going to introduce other ways. Well, there's another way. You know how to use Excel to do it, right? But what I want to do is also show you how to use the T table to do it, which is the table that you got last day or the day before. I can't remember. To find the areas, we can use the Z table. We can use Excel. Like obviously the internet, other software, blah, 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 blah. That goes without saying. But for us, we're going to limit it to 3 options. And so we could use the T table. Now, I am going to focus on using the T table. And the reason for that is you're already very comfortable with using the Z table, so that makes sense. But if we start using the T table, we'll be able to use the T table when we also start calculating T's. And so then the same approach applies. So although we're kind of doing it a little bit differently, then you'll be able to apply the same approach later on. So I think that's nice. Now, for our first example, I'm going to show you with the Z table and the T table. And for our tests, you're allowed to choose whichever one you'd like. I don't care. I'll use the T table in my examples after the first one. But if you prefer to use the Z table, that's totally fine. Just know that we're going to have to use the T table. So why not get used to it, right? And on the assignments, it'll tell you using the Z table or using the T table. So you have to be able to do both. Or using software. Rude. So I will use the T table so that we learn the methods that we'll use later on for other test statistic or for the T statistic. So we can apply the same methods to the T distribution later on. Otherwise, we'd have to learn a whole new way of doing things, and it's not very nice. And if you need the exact value, you can always use Excel or some online calculator or whatever, right? And so, again, without an example, it's all theoretical, right? And so I guess with that, we're ready for step 4. Step 4, oh, that sounds good because we only have 4 steps. But what is step 4? Step 4 is the conclusion. On the plus side, there are only two possible conclusions, okay? And they depend on how the p-value, if the p-value is small enough or not, okay? But also, yeah. So only two options, but there are 3 steps within the conclusion. So that's why I say you could make it 7 steps if you, or 6, I guess, if you really wanted to make as many steps as you want. And so step 4, the conclusion at its heart is if the p-value is small enough, you have enough evidence to reject H naught, right? If the p-value, let's focus on this one because it's easier to wrap our head around. If the p-value, this area is small enough, means this, my sample proportion is far enough away to be able to say, unlikely that P is P naught. It's probably something else, probably greater than P naught, right? And so that's what we're going to be relying on. So if the p-value is small enough, that's tricky. How do we know if it's small enough? We need some threshold, right? Less than, so here I'll use less than do I do it now? The significance level, I'm doing it. Less than the significance level, which is also called the alpha level, or alpha level. Alpha's a little fish. Guess I should write that alpha. So less than the significance level or the alpha level, which has a default of 0.05. The default alpha is 0.05. Most questions will say, use a significance level of 0.01, use a significance level of 0.05, 0.1. If it doesn't say, you use 0.05. It's directly linked to the default confidence level being 95%, right? I'm either 95% confident that it's somewhere in here, or there's a 5% chance that I'm wrong, right? That's the link. Okay, but so if the p-value is small enough, so less than 0.05 or 5%, okay, we have enough evidence to reject H naught. If you're rejecting H naught, and let me, should probably say in favor of what? Well, I reject that, and then you walk away. No, can't do that. Reject H naught in favor of HA. And then the third part, and I'll break down these parts, but the third part of the question, or the conclusion rather, is what does that mean in terms of the question? What does rejecting H naught mean in terms of the question? In our case, right, if we rejected the null hypothesis, then for the voting example, for, I don't know, for example, then we would say significantly more than 50% of voters, right, are predicted to vote for this candidate, right, or a majority. And so, of course, the conclusion in terms of the question, trying to keep it on the same page. So there are 3 parts. Now here, oops, or maybe I should introduce what I'm doing here. The conclusion always consists of 3 parts. First part, you compare the p-value to the alpha level, right? Is it less than the alpha level or is it not less than the alpha level, right? 2 options, that's it. And so you're going to compare the p-value to the alpha level. If it's small enough, you have enough evidence to reject H naught. So then the second part of this conclusion is you either have enough evidence to reject H naught or you don't, okay? And so the wording there is really important because we did all our testing assuming that the null hypothesis was true, right? And there's a chance that we're wrong. There's a p-value chance that we're wrong. So you never, ever, ever say anything like, I accept the null hypothesis, because you have to understand that there's a chance that you're wrong, okay? And so then your conclusion in terms of H naught, right? You either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. Okay. Oops, newer. Never say you accept a hypothesis, right? And maybe I'll throw in a U here. Never say you accept. If I see the word accept, I will take half a mark off. Well, I've said it. So it's fair game now. You do not say accept. Why? You never say you accept a hypothesis because there's a p-value chance that you're wrong, right? In fact, more broadly, we're allowing for an alpha level probability of being wrong. Maybe I'll say that. Because you allow for an alpha level probability of being wrong. So there's a 5% chance that you're wrong, right? And so you don't want to say that you accept something because we don't know. All we can do is use the probabilities and say, no, it's unlikely, so I reject it, right? Good. And then the one that everyone loves to forget about is the conclusion in terms of the question, because you've done so much work up until this point. You feel like, oh, I'm done, right? But you have to reword the question as an answer, right? Is there enough to say, is there evidence to say that a majority will vote in favor of this candidate, right? Yes or no. So then you have to state your conclusion, oops, in terms of the question. So because we can't accept a hypothesis, we have to either reject a hypothesis or fail to reject a hypothesis. Then the only 2 options for wording our conclusion is, so we have 2 options. There are only 2 options for our conclusion. Time flies when you're having fun, huh? Hey, I've still got time. Okay. So there's only two options for our conclusion. The first one, I'm going to write out, and then I'm going to copy it and just edit it. Think about that. Edit it. I edited it. Try it. It's hard. Option one. The p-value is less than the alpha level. Let's start there. So if the p-value is less than the alpha level, or the significance level if you prefer, we have enough evidence to reject H naught. Oops. Evidence to reject H naught in favor of HA. And then, of course, what does that mean in terms of the question, right? And then your conclusion in terms of the question. Now, in terms of marks, your conclusion is 3 marks, typically out of 7. And so that's a good chunk of your marks, right? And so it is going to be linked to 1, 2, 3. You don't want to miss that conclusion in terms of the question. Okay. So that's the first scenario. The p-value is less than the alpha level. I have enough evidence to reject H naught. And then I'm going to just copy this and edit it in red. Call this option number 2. What's the other option? The p-value is not less than the alpha level. That's fine. That can happen. It means that they're close enough together to not be significantly different, right? So it's not less than the alpha level. So then we do not, oh, that says do, but it looks like boo. Then we do not have enough evidence to reject H naught. Now, although technically saying in favor of HA is not incorrect, I don't like seeing it, so I'm going to scratch it out. If you don't have enough evidence to reject H naught, that's the end of the story, right? And then what does that mean in terms of the question? So those are your only 2 options. And so that's why I like to use this sentence structure of if the p-value is less than the alpha level or not less than the alpha level. You either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. What I want to do is skip ahead. Uh-oh, I missed decision errors, didn't I? Oh, well. I want for you to try this. Obviously, we're going to go through this example together, but for Thursday, try this on your own for Thursday. See how you make out and enjoy. If you have any questions, let me know. Otherwise, I'll see you then.